So as you know, carbon exists in the free form in forms of allotropes, which are diamond, graphite and fullerenes. So what is an allotrope? Allotrope is actually the existence of different forms of the same element which are having different physical properties, but chemically their reactivities will be different. So let's have a look into the diamond and its structure. So when you consider diamond, let's consider carbon, as we have already discussed in the last video, that carbon is having an atomic number 6, indicate 2, 4 will be the electronic configuration. So now when you consider the carbon, valence shell has 4 electrons, and you know that only valence shell electrons can take part in bonding because all the inner electrons are actually well shielded from the valence electrons. So now when you consider the valence electron, let's indicate the carbon atom like the dot or represent it by Sc. So consider the carbon and represent their 4 electrons which is present in the valence shell. And in diamond, it is observed that each carbon is tetrahedrally bonded to 4 other carbon. And therefore, in the carbon, when you consider diamond, each carbon has no free electrons as 4 electrons are taking part in bonding. Let's consider the neighboring carbon. Again, you have 4 electrons and they are also bonded to 4 different carbon. So, when you represent the diamond, the structure is actually network structure. Let's represent the dot as the carbon, and it is tetrahedrally bonded to the next 4 carbons. Again, the individual carbon is bonded to 3 more carbon. So when you represent this structure, you are having a 3-dimensional network structure. So 3D network structure of diamond makes the diamond hard. So this is the reason why diamond is hard and is used for cutting the materials like glasses. Now when you consider the conductivity, will they be able to conduct electricity or not? That's a question. So when a system is conducting electricity, either there should be the presence of mobile or free electrons, or free ions should be able to move. So when you consider here, as all the 4 electrons present in the valence shell of carbon is already taking part in bonding, there is no delocalized or mobile electrons, and hence they are non-conductors or insulators. So this non-conductivity is due to the absence of free electrons. So whenever you consider an atom, as you know from the modern theory of quantum mechanical model of atom, each atom has several electrons, and that electron is present in several rooms called atomic orbitals. So atomic orbitals are the 3-dimensional space where the electron's probability is maximum. So now the electrons are present in the atomic orbitals, and they can be considered as the rooms. So these atomic orbitals are of 4 types. You have s orbital, p orbital, d and f orbital. So when you consider any electron in an atom, that electron can be present in s, p, d or f orbitals. So let's consider the carbon. In the case of carbon, when you consider the electronic configuration is generally written in accordance with their energy level. So when you consider the energy order of S, P, D and F, it is given that for the same energy shell, the order is S, P, D, F, where F will be at a higher energy. And hence, if you consider the first orbital, and that is represented by 1, and you have s orbital in the first shell, which is indicated by 1s. When you consider the second shell, let us consider the second shell, as you know that, let us consider this as the first shell. When you consider the second shell, their area is maximum, that indicate they are able to accommodate more rooms or orbitals. So if you represent the second shell by 2, the second shell has 2 types of orbitals, and they are s and p, which are indicated by 2s and 2p. Go for the third shell, you have 3s, 3p and 3d orbitals. When you consider the fourth shell, even you have a bigger area that indicate they are able to accommodate more and more orbitals. So let us consider 2s and 2p. According to this, as you know that when you consider sp-df orbitals, p will be at a higher energy compared to s. Now when you are going to fill the electrons, lower energies are filled first, because then the soft-formed system will be having less energy, and hence that makes the system more stable. So we are discussing about the diamond. When you consider carbon, its electronic configuration is written as 2, 4 as the atomic number is 6. According to modern concept, these electrons are present in the shell. Obviously, when you consider the first shell, you have 2 electrons. And in the first shell, you have 1s is the atomic orbital represented according to quantum mechanics. So when you consider the 2-4 electronic distribution, the 2 electron is present in the first orbital, and that is indicated by 1s2. And when you consider the second shell, L shell, they contain 4 electrons. And for the second shell, again you know that it has 2s and 2p. S being the smallest orbital can accommodate only 2 electrons. So they accommodate 2 electrons from the 4 valence electron. Now the remaining 2 is accommodated in the p orbital. And hence, when you consider carbon, their electronic configuration according to modern concept is 1s2, 2s2, 2p2. So carbon is forming 4 bonds here. So whenever they are forming the bonds, they try to modify their atomic orbitals. So as we have already said, when you consider the 4 electrons present in the valence shell, they are actually present in the 2s and 2p orbitals. Now let's represent that 2s and 2p orbitals. The 4 atomic orbitals are s, p, d and f. S can accommodate maximum 2, whereas p, you have 3 types of p orbitals are available. Each orbital is able to accommodate 2 electrons. So that indicate total 3 orbitals will gives you 6 electron, and hence whenever you consider the p orbital, its maximum capacity is to accommodate 6 electron, because each orbital accommodates 2. Whereas when you consider s electron, they are able to accommodate only 2 electrons because they are of only one type. Consider d orbital. You have 5 types of d orbitals. Each orbital accommodates 2 electrons. That indicate total 5 orbital will give you 10 electrons. And hence, maximum number of electrons that can be accommodated in the d orbital is 10. Go for the f orbital. There again varieties of f orbitals are available, and you have 7 types of f orbital. Each orbital will be giving 2 electrons, and hence you have a total of 14 electrons. So when you represent carbon, and that is we are representing only the valence shell 2s and 2p, you have 2s and 2p. 2s should be only of one type, whereas 2p, as they have maximum of 6 electron capability, they are of 3 types, and this is the representation. Now let's fill the electrons. 2s has 2 electrons, so that electron is indicated here. Whenever you consider a paired electron, one will be in the clockwise direction, one spin, whereas when you consider the next electron, their spin will be in the opposite direction. Consider 2p. As you have 3 orbitals of same energy, you need to fill 1 electron in the first orbital. Then the second electron is not getting paired up, instead they are getting filled in the next orbital. So this is the representation of carbon in the ground state. What happens to the carbon electrons when they are going to form the bonds? So let's have a look into that. Just have an idea that carbon 2,4 was the representation we used, but now according to the modern concept, we are introducing the atomic orbitals, and its representation is 1s2, 2s2 and 2p2. Whenever you consider bond formation, only valence electrons are taking part in bonding, indicate let's represent only the 4 electrons, and that is present in the 2s2 and 2p2. S can accommodate maximum 2, P can accommodate maximum 6, as you have 3 orbitals, and whenever you fill the electrons in the degenerate or same energy containing levels, pairing happens only after the partial filling, and hence when you represent 2p2, 2 electrons are not getting paired up, instead they are partially filled in the orbitals. Thank you.